Okay, well, good morning and happy Friday to everyone. Hope you're having a productive week of ATPESC so far. On behalf of all of our lecturers today, I wanted to welcome you to track 3 of ATPESC. As Ray said, we're focusing on data-intensive computing and I/O today. And what we want to try to do is teach you a little bit about how HPC storage systems work. They're a little bit unusual compared to other storage systems you may have access to. Maybe we can learn a little bit about how to access data more efficiently from your application, and also learn more about what data management tools are available and how to use them. So the way we're going to approach this, you've got access to the agenda with details in it, but the general idea is that in the morning, we're going to cover some kind of introductory kind of general concepts so that you have sort of the foundation for why we're teaching you the tips and tricks that we're going to do later. They'll make more sense if you kind of understand the underpinnings of why we do what we do. From there, we'll go up through things that are a little more application oriented, some interfaces that you can use to access your data. And then in the afternoon, we'll get into details of kind of some case studies of how to tune the I/O in your application and how to sort of manage your data and transfer it around. So generally, we're going to kind of start with some general stuff this morning and then work our way up to details. So if you find that we're talking about stuff you already know, I'm pretty sure at some point we'll hit something new and interesting for you. So stay tuned for us. A little bit about our lecturers today. Ray introduced myself and Rob Latham. But there's 3 of us from Argonne. I'm Phil Carns. We've got Rob Latham and Shane Snyder. All 3 of us are developers in the Math and Computer Science division at Argonne. And between the 3 of us, we cover kind of a broad spectrum of I/O topics in scientific computing. So Rob is sort of our expert on kind of how applications use the storage system and sorts of interfaces they would use. Shane Snyder has a lot of experience in kind of characterizing and understanding how storage systems work and how the applications use them. And all 3 of us have worked on kind of distributed, data services, kind of new forward-looking things for how to make best use of storage hardware. We're also pleased to have 3 guest lecturers today. Scott Breitenfeld is from the HDF group, and he's done a lot of things at HDF over the years, but a lot of it is focused on sort of troubleshooting and tuning HDF for HPC applications. And he's also done some work with third-party libraries to help tune them to make best use of HDF5. We'll learn more about HDF when he speaks this afternoon. And Suren Baina is a scientist at Lawrence Berkeley Laboratory who works on HDF5 as well in the context of the XIO project, which the goal of the XIO project is to tune HDF5 specifically for exascale, so kind of pushing it in that direction to run even larger problem sets. And he also works on the Proactive Data Containers project, which deals with managing data in deep storage hierarchies. So you'll see how that's increasingly relevant with the machines we have now. And finally, we have Vas Vasiliadis of the Globus group. He works a lot with customers and teams that are trying to learn how to use Globus and get the most out of the technology that's available. So he's going to have some good insights for us on that. He also has teaching experience at the University of Chicago with cloud computing and product management. So if you take the 6 of us all together and look at what it is look at what we do and why we might have some good ideas for you to consider today. Basically, the situation is there's a lot of high performance storage devices available on the market. You can go buy some really great, flash drives and NVMe drives and persistent memory and all sorts of different things. But there's a gap between buying a bunch of hardware and getting scientific applications to use them effectively. So we work on kind of bridging the last mile, kind of making that leap between a big pile of fancy hardware and things that you can actually get productive science results out of. So the kind of things we do to make this happen is building and optimizing data services, running the data centers, looking at how the storage is used and kind of predicting how it will be used in the future so that we can plan. And in general, just kind of putting the new storage technology into the hands of scientists. So a little word on logistics for today. You guys should know how to find the agenda already. I'd encourage you to ask questions as we go. That'd be great to have some interaction during the day. And we'll also be monitoring the Track 3 Slack channel. At least one of us will be watching it. And in some cases, we'll be able to kind of help one-on-one if you have some technical questions, and also they can help relay questions to the lecturers who maybe can't watch so many things at once. We do also have some hands-on exercises. You'll see a link at the top of a lot of the slides today. It's on GitHub, and you can clone those and look at them wherever you'd like, but they're set up mostly for Theta and Ascent. We have a dedicated reservation on both of those systems today during the day. So you're welcome to kind of try things out there. Unfortunately, we don't really have a lot of time blocked for specifically, working on particular hands-on exercises. So I'd encourage you to look through it. If you hear something today that you want to learn more about, look and see what exercises we have to go with it and try them out and ask questions. We'll try to monitor the Slack channel through the rest of the ATPESC program as well. So if you don't get to it today, that's no problem. We can help you out later. So that's sort of the logistical aspect for the day. Does anybody have any questions before we get going on our technical content? All right.
I don't see any questions, Phil.
I've either put everybody to sleep already or we're ready to go. So we'll jump in here with the kind of the first technical material. This is the principles of high performance computing I/O. So I mentioned that we wanted to start with some sort of background concepts, and I'm hoping that this kind of informs why we do the things that we do a little later in the day. So we'll start with a little definition first. What is HPC I/O? What do we mean by that? And this is just storing and retrieving data on a high performance computing platform. Almost always this means using a parallel file system. So parallel file systems are designed to quickly store and access enormous volumes of data, gigabytes, terabytes, petabytes, that, scaling up, no problem. And to do that, they have to orchestrate data movement between a lot of different parties, the application itself, the system software, and the storage hardware. And this is important to get right because, as you guys know, CPU time on these high performance computing platforms is very precious. So if your compute cores are just waiting for data to be fed to them or waiting for data to get out, then you're wasting resources that you have. So we want to do a good job of this. So the majority of the material today is really about how to take good care of these parallel file systems and get the most out of them. So why are parallel file systems interesting? First of all, they'll look just like any other file system you may have on your laptop or any other computer. You have directories and files you can open and close and read and write. So all of that's fine. Shouldn't be too unusual. But they don't behave like a conventional file system, and we'll get into why. And I'm going to highlight kind of 5 crucial things to keep in mind about why a big parallel file system might be different from another file system. And we can kind of revisit these concepts through the day to kind of explain, the reasoning behind some of our optimization and usage tips. So the first thing I wanted to talk about with HPC I/O is that you can select between several file systems on a big computing platform, like at Argonne or Lawrence Berkeley or Oak Ridge. And I'll start with kind of a metaphor here, but if file systems were vehicles and you were looking at the range of vehicles that were available, you might want to pick one to hold a lot of cargo. You might want to pick the one that's the fastest possible. You might want one that's easy to bring your friends along with you to do something. You might want the safest thing if you have really critical data. You might just want to make a quick, short trip and not bother with a lot of fuss, extra steps. if we're talking about vehicles and you can see all the vehicles laid out in front of you, it's probably intuitive which one is going to be the best for each job. If you actually wanted to do this with a file system, though, these are what your options look like. You have all sorts of different names: scratch, you have environment variables, $scratch, you have home, projects, all sorts of different things. Now, if you're just looking at that list, do you know how to pick which of these is the best to hold the most cargo, which one's the fastest, which one's the easiest to work with people on, which one's the safest? It's not as obvious as it would be if we were picking a vehicle. So the thing to kind of, I'm not going to try and tell you what every file system everywhere is best for what job, but what you need to do is remember that your facility documentation covers this stuff. So I've got links there, and you should be able to find these in the documentation for any given compute platform. But you have to refer to that and see what the capacity is, what the quotas are, what is the backup policy, and help, ask questions from the facility staff if you need to figure out what's best. And one thing that you may find frustrating if you're moving across facilities is that they aren't consistent about, what the different names of these things are. So /project and /projects are two different things at Berkeley and Argonne, and /scratch and $scratch are two different things at Berkeley and Argonne. They're not the same at all. So don't assume that if you know which file system is best at one site that you know which one's going to be the best at another one. And just to kind of go a little further on this, if we took those same 5 vehicles again and looked at the controls, what kind of steering wheel is there? What kind of brakes are there? What kind of gauges do you have? You can probably tell by looking at the interface to that vehicle, basically what is it going to be? What is it kind of optimized for? What does it have controls for? If you did the same thing for our file system examples, here's your interfaces that you have for all these different, radically different in some cases, file systems. Unfortunately, they all look the same. They all let you open, close, read, and write files. So that makes it hard to tell which is which just by looking at the interface. Again, look at your facility documentation. So the good news is this is good for portability. If you write your application for one file system, it's pretty much going to work on any file system. So that's a nice thing, but it's not going to work the best unless you choose the file system that's really going to work well for your application. Okay, so the second thing I wanted to talk about is kind of what's going on inside of these file systems and how does that make them behave differently. So I've got a diagram on the right side of this slide. It's a few years old at this point, but this shows the Scratch file system at Lawrence Berkeley at that time. And the interface we talked about already looks like any file system, but you're very likely to have at least 10,000 disk drives within that file system. And that's not an exaggeration. That's a pretty common number for this class of parallel file system. And to take that many files, hard drives or flash drives, and mush them together into one thing, it takes some pretty specialized hardware and software to kind of do the aggregation and make it look like a unified thing. And this kind of technology that's under the covers makes them act a little differently. So the particular thing I want to call to your attention is, imagine that you are executing on a compute node, one of these top blue boxes here. That's where your application is running, and you want to access some data on disk. You're going to go from your application process to the operating system on the compute node, to a forwarding node on the fabric, to an external network fabric, to a file server, to a disk array, to a hard drive, and then all the way back up to get your data to the application. So there's a lot of hops to get from where your application is running to where the data is in many cases. Now all that hardware is very fast, but there's no getting around that there's a long chain to get to your data in many cases. And what this means is that the latency, or the time it takes to get 1 byte of data from your application to a disk drive or vice versa, it can actually be pretty bad. In fact, quite a bit worse than a laptop, or maybe even worse than your phone. And this sounds like a bad thing, and to be honest, it is. But the good news is there is just a ton of compute nodes and a ton of network fabric links, and a ton of file servers available that you can use simultaneously. And what that means is that the aggregate bandwidth for big parallel data accesses is just enormous. You can move a lot of data all at once. So a lot of what you're going to hear today is trying to understand those strengths and weaknesses. You almost always want to move data in parallel with big operations when you can, when that's possible. And you want to try to avoid waiting on individual sequential kind of small operations when you can. So that's kind of in a nutshell what a lot of the optimizations we'll talk about today are trying to do is do the things that the parallel file system is great at and avoid the things that it's bad at. The third thing to call to your attention is the issue of data models in high performance computing. So as you guys know, I was watching some of the bio slides from you guys before the presentation started today, and I know you're working a ton of different interesting scientific fields, but that means that your data is going to be diverse and complex. You may have multidimensional arrays, you may have multiple variables at each sample, you might have images, scan lines, all sorts of different things that you're working with. And not only the data itself, but there's going to be descriptions of that data, which we call metadata. And that could be headers, attributes, timestamps, names, all sorts of things that help you kind of keep things organized. So that's what you want to work with ideally. But if you look at what a parallel file system provides, it doesn't have any of that stuff. You get a tree hierarchy. You get containers with just a linear stream of bytes. Those are files. You get containers that can list other containers. Those are directories. And so somehow you have to map between what is sensible for your application to what can actually be stored on a generic file system. So you could do this yourself. You could say, well, I've got a frequency attribute. It's an 8-byte float. It's a gigahertz value, and I'm going to store it at offset, 4096. And that will work. But you can imagine how things could go wrong if maybe someone else comes in behind you and wants to modify something, and they're trying to find documentation. Maybe they don't realize the implications of where things are stored in a file. So this can be a challenge. And so what we'll recommend a lot through the day is using a data library. And there's a lot of examples out there. 3 of the most popular ones are HDF5, ParallelNet CDF, and Adios. But there's other ones, some that are very specialized to particular problem domains. But the point of these data libraries is to bridge this gap between application data models and file system data models for you. And why would you want to do this? So first of all, you can get a more expressive interface for your scientific data. So instead of operating in terms of bytes, you can use typed data and structs and arrays and attributes and things like that that might make more sense for the nature of what you're doing. The second is interoperability. If you use one of these data libraries, you don't have to memorize and document what's at offset 4096 in your file because you're using a higher level interface that does that for you. And so even if you store a data set and someone comes back to it 5 years from now and no one's looked at it, it can be inspected. There are tools that can show you what types of data and what the names are in an HDF5 or ParallelNet CDF or Adios file. So someone can come back later and find that without digging up your code necessarily. The third issue is performance. Not only doing the data type translation, but these libraries often bake in some optimizations that are particular to platforms. So if you use HDF5 on one system and HDF5 on another system, it may do a little bit different things under the covers to try and handle how to organize and how to aggregate things best for that platform. And then I sort of mentioned this already, but future proofing is a big deal because these are documented data formats that you can come back to in the future. Even if the storage devices go away, even if the platforms go away, the data should still make sense. Then moving on to number 4, I touched on this a little bit already, but there's a handful of different vendors that can build the types of high performance storage systems that you need for scientific computing. And they're often custom built for the needs of a particular site and what sorts of applications they run there. So you likely have different hardware, maybe it's new cutting edge stuff when the system's first deployed. You might get different software. And there's basically a lot of different ways you can put together a storage system, and this leads to different performance characteristics. So the reason I want to warn you about this is that if you kind of hyper optimize your application for, say, the Theta system at Argonne, that's great. You know, you may get a considerable performance improvement, but that doesn't necessarily mean that you're going to have it tuned great for the Cori system at Lawrence Berkeley Laboratory, for example. So the key takeaway is that it's not just a one and done kind of tune your code and that's it forever. We want to teach you some portable tools and libraries that can do things differently on different platforms, so you can kind of adjust and kind of, you know, ride the wave with where you have compute time to run. And there's some sort of core debugging principles that, you know, they're not super hard, but if you kind of understand these things, then you'll be able to adjust. And I'll give you an example of how these things can look different on the platform. So when we talk about the I/O subsystem of a big HPC system, we can often think of it as sort of a set of layers. So at the very bottom, you have the I/O hardware. This is your disk drives and your network and so forth. At the very top, you have your application that's running your computation that you're interested in. And translating between these things, there's something that supports your data model, a high-level library like I mentioned earlier. There are things that do transformations on that data to kind of organize it better for the storage system. That could be MPIO or an IO forwarding system. And then you have your parallel file system that takes that data and distributes it across the hardware. So if you look at our previous generation system, this system doesn't exist anymore, but this was the Mira Blue Gene system that we used to have at Argonne. The high-level libraries were, you know, things like HDF, Parallel Net CDF, and Adios. The transformations were done by IO middleware like MPIO, an IO forwarding system built by IBM called CIOD. And we had a parallel file system called Spectrum Scale. So that's kind of what the stack looked like on that system. If you look at what we have now, some important things changed. The CIOD isn't there anymore. Instead of that, we have something called LNet routers. You don't need to worry about exactly what those are right now. And the parallel file system changed. It isn't IBM Spectrum Scale, it's something called Lustre. So the LNet routers and Lustre behave a lot differently than CIOD and GPFS did. But if you notice, the top level of the stack didn't change. Hopefully you have the same application, of course, but also you have the same data model libraries available, HDF5, Parallel Net CDF, and Adios. So the kind of higher level you can work with your application, the more likely you are to be able to kind of adjust as things change on different systems. And not only that, if you look to the future, we don't know what the future is going to hold. There's different technologies coming up, and I'll touch on some of these in the next segment. But it may not even be files at all. It may have object storage systems. There's different kinds of devices we could have. There could be key value storage. There could be new file systems that aren't deployed yet, but are coming. And so you can kind of adjust to this if you try not to optimize too much yourself for these particular technologies, but use some tools to help you get there. And then last but not least, I want to explain kind of performance variability on HPC IO systems. So the issue is when you run your job one time and then you run it again, you may not get the same IO performance in one job as you did in the previous job, even though nothing really changed. And so why is that? As I mentioned before, there's thousands of hard drives available in most of these storage systems. You'll never get 10,000 hard drives to all perform perfectly at the same time. You just can't. There's too many factors involved in why a given hard drive performs the way it does. The second thing, and probably the biggest issue, is that you're actually sharing the storage system with many other users. So when you allocate a set of compute nodes, you get dedicated access to those compute nodes for the duration of your job until your time runs out. That's not true of the storage system. The storage system is shared with some exceptions that we'll talk about. But that if someone else is running a huge job that's accessing petabytes of data, then that's going to influence your ability to run a smaller job that's accessing gigabytes of data, because they're just competing for resources to some degree. And it's not just other users, but it can be other systems. So at the ALCF, for example, we have project file systems that are connected to Theta, Theta GPU, Cooley. They could be doing wide area transfers, or they could be doing archive access. And so a lot of things could be kind of putting pressure on the storage system at any given time. And to give you an example of what this can look like, this data is a little bit old, but the point is still valid. We ran 15 benchmarks, 15 copies of the same benchmark at 6,000 processes on the Edison system, which is the previous generation system at Lawrence Berkeley National Laboratory. And we measured how long the I/O took. So sometimes it took as long as, say, 63 seconds. Sometimes it completed as fast as 51 seconds. And we plotted all 15 samples using kind of a box and whiskers with the min, the max, the median, the quartiles. And so if you look at this data, imagine that you've run your application one time, you've got a performance number, and you make an adjustment that you think will make the I/O access go a little faster. And you run it again, and it could be 10 seconds faster. But how do you know that that change was because of your modification to the application versus just changes in the system behavior since the last time you ran your job? The fact of the matter is you can't tell. There's no good way to get a handle on that right now, except to run multiple runs and kind of get a feel for what the trends are in your application. So I just want to warn you about that, especially as you're doing your hands-on today. It's possible that things that you expect to be identical each time will not quite be. And we actually have a hands-on exercise that focuses on the variance phenomenon if you want to see what it looks like on the systems we have now. So that's the 5 things. I'll kind of recap here and put it together for you. These are the general ideas to keep in mind through the day. The first is that you need to look at your facility documentation for wherever you're running to find what storage resources they have and pick the best one for what you want to do. Once you've done that, the key thing to use most of these systems quickly is to move big data in parallel, use big chunks, do things concurrently, and avoid waiting for individual small operations when you can. You can use high-level libraries and data management tools to help with this when it's possible, so you don't have to do all the work yourself. There's some general purpose kind of debugging tools and techniques that you can reuse across systems, and Shane will cover some of that later in the day. And just be aware that also that I/O performance might fluctuate through no fault of your own. It may go up or a little bit down. So you might want to kind of track your I/O time, over time, and see what the real underlying trends are. And so kind of one last thing, we hope that we can teach you some straightforward things you can do to make the best use of your storage systems, but it's really an ongoing process. One way we like to think of this as an OODA loop, kind of a control loop for how you can kind of iteratively improve how things are working for you. You can observe your application, and we've got tools to help you do that. There's one that we'll highlight shortly called Darshan that can help you see what your application is doing in terms of its I/O access. Once you kind of have that information about how fast is your I/O and how much are you doing, you can kind of orient that with respect to background information, stuff from this presentation just now. What does that mean in the context of how these storage systems work? You can decide how to improve that using facility resources, so the documentation and your support staff at the facility that you're running at. And then, once you kind of have all that, you can make a decision and then act on that to implement an improvement in your data access. So this is going to be optimization techniques that we teach you today, tools and libraries that will help you improve matters. And then it starts over again. You loop back around, you observe, orient, decide, and act again. And that is it for the principles of I/O. I can take some questions if anybody has any before we go to the next topic.